Today we will do an important theorem called the compactness theorem, which you will see some of the consequences of compactness, and it is something that this compactness is actually very closely related to the topological notion of compactness, and it is possible to say, it is possible that it is possible to show that this compactness is really the same as the topological notion of compactness, either defined through metric spaces or through neighborhood spaces, whatever. So, this compactness theorem, but we will look at it independent of topology, we will just look at it as in its isolation. And so, and it is we will see the importance of that. So, the main thing is, what does, supposing you have an infinite set of sentences and you want to know essentially by infinite, of course, since we are talking about a logical system, it is we mean only countably infinite. So, denumerable, we are looking at denumerable sets of sentences, and essentially if you look at the satisfiability of infinite sets. So, essentially from these corollaries 9.4 and 9.5, which essentially says that. So, now when you are talking about infinite sets, there is no guarantee that your tableau construction would be finite. Okay. So, but we can always take the notion of that tableau to infinite. A tableau is just a tree, we take the notion to infinite trees, that is as simple as that, right. So, these corollaries 9.4 and 9.5 say that if gamma is satisfiable, then there exists a completed tableau rooted at gamma which has a satisfiable leaf, okay, and a set gamma is unsatisfiable if there exists a closed tableau rooted at gamma, right. But the corresponding notion for infinite sets would be that, okay, if an infinite set is unsatisfiable, then you should definitely get a closed tableau, or there should be at least one closed tableau. Okay. But if it is satisfiable, then there would be essentially be some kind of infinite tree. But the problem with any finite point of that infinite tree is you do not know whether it is going to close at a later point, right. So, there is a problem when dealing with these issues for infinite sets, and so what we would like to do is we would like to look at this notion of satisfiability of infinite sets, and satisfiability as far as we are concerned is the same thing as consistency of an infinite set of sentences, right. So, essentially, so these are the questions that it raises. Suppose gamma were a denumerable set, under what conditions is gamma satisfiable? Suppose every subset of a denumerable set gamma is satisfiable, then can you say whether gamma is necessarily satisfiable? The whole point about dealing with any kind of infinity is to either get a finite representation or to get approximations in terms of finitary objects. So, the construction of let us say irrational numbers or real numbers by Dedekind cuts is essentially as looking at finitary intervals or at least intervals with endpoints, and trying to represent, let us say, real numbers as limits of those. So, limits and continuity are the most important notions when it comes to infinite sets in any branch of mathematics. Yeah. So, one question is whether you can always approximate something infinite by a possibly infinite set of finitary approximations. So, that this infinitary set, each approximation is finitary, but the set itself might be infinite. So, essentially you have some limit construction which tells you that, okay, if this limit exists, then okay, so it is, then this infinitary object is essentially been captured, and that is exactly what has been happening throughout the history of mathematics ever since the start of the subject of analysis. Yeah. So, this question too essentially is asking whether this infinitary object this infinite set of sentences, its satisfiability can somehow be expressed in terms of finite tree approximations, satisfiability of finite subsets. Yeah. Then of course, the converse question is that is related to the topological notion of continuity and limit. Does a limit exist? Sometimes under discontinuity those limits do not exist. So, here suppose only finite subsets of a denumerable set gamma are satisfiable, then what can you say about the satisfiability of the whole of gamma? That is yeah. So, these are the kind of questions that actually come up when you have in any branch of mathematics when you have some infinitary object, and this also includes all branches related to mathematics, like this also happens in the case of trying to find the semantics of recursion in programming languages, for example. So, it has a wide kind of applicability. The kinds of methods that are used have a wide kind of applicability, right. Okay. So, now we have to consider trees in some generality. Okay. We have to be prepared to deal with infinite trees. Throughout our data structures and algorithms kinds of courses, trees were always finite, but now but for example, you have actually come across infinite trees when you define this SOS semantics of a programming language with values. What an SOS semantics generates for a program is for the dynamic behavior of the program is essentially an infinite tree, right. And so, the program itself is a finite object, that is a finite abstract syntax tree, but the behavior of the program, the execution behavior of the program is essentially an infinite tree, right. So, let us look at trees and let us also specify some of our notation and terms. So, we are interested really in not unordered trees, but so I am distinguishing between unordered trees and rooted trees. Okay. Unordered trees are the kinds of trees you get in graph theory, okay, which is not necessarily the same as the kinds of trees you get in let us say data structures and algorithms. So, all the trees that we deal with in computer science usually are rooted trees. So, our abstract syntax trees are rooted trees. Execution behavior of programs are all rooted trees. They start from a starting point, and then moreover all the edges in these trees are all directed edges, and they are not undirected edges. So, we will look at a rooted tree. So, a rooted tree essentially consists of a set of nodes n and an edge relation which I will represent by an arrow, and of course, a distinguished node called the root. Such that of course, every node other than the root has some what might be called a unique predecessor, and there exists a function called the level function, which for the root gives you a 0, and for any given an edge from S to T, where S and T are both nodes, then the level of T is 1 more than the level of S. Okay. So, this ensures, I mean these things, the fact that L is a function and the fact that you have an exact notion of successor here and predecessor here essentially make it clear that this a rooted tree is for example acyclic, and it does not have any self loops. Nodes do not have self loops, and then this function essentially guarantees that the nodes are not sort of repeated. Yeah. So, that you cannot have multiple copies of nodes. So, it is like the standard notion of trees that you encounter in data structures and algorithms, that like binary trees and so on and so forth. And of course, the only difference here is that this set n could be infinite, right. So, you can have a tree with an infinite set of nodes, it need not be finite. Otherwise, it is a standard set of standard notion of a binary tree or a multi-way tree that we have. Okay. So, the basic facts are that this edge relation is irreflexive, okay, and the root has no predecessor, and there is a notion of a leaf node, which are in the case of finite, in the case where trees are finite, there is a the leaf nodes do not have successors. I mean that is. So, so we also talk about trees rooted at some r, and the usual notion of a path. Okay, in this case we define a path as always starting from the root. Yeah. If it does not start from the root, we can talk about a segment of the path, or we can talk about a path starting from the root of a subtree rooted at some node, and so on and so forth. So, okay. But otherwise, in general, when we talk about a path, we will just talk about a path starting from the root. So, essentially you traverse the arrows, traverse the nodes, so that each you go through successor nodes, some sequence of successor nodes. So, since our trees can be infinite, so your path can also be finite or infinite, right. And we will talk about a branch as a maximal path. So, it means you do not start anywhere, you do not stop anywhere, you go through the full path from the starting from the root. And then we have this usual notions like successors of a node, okay, predecessors of a node. And since this arrow, the edge relation is irreflexive, we can consider the transitive closure of the edge relation, we can consider the reflexive transitive closure of the edge relations, and so those will just be represented as arrow plus and arrow star respectively. Okay. And you can talk about the descendants of a node, which I will represent by DAC. We can talk about ancestors of a node, and of course, the root node has no ancestors. We can talk about subtrees rooted at some node, and we can also talk about a tree being extended at the leaves to another tree. Yeah. So, what I have in particular, I have said that when we talk about a tree, we are talking about this edge relation in such a way that the tree is, well, in graph theoretic terms, it is at least weakly connected. Okay. So, there are no isolated nodes, there are no subtrees disconnected from other subtrees, and so on and so forth, right. Okay. So, I have a subtree rooted at a node also means that we are essentially restricting the set of nodes from n to all the descendants of that node n. So, that is why the subtree T prime here. So, I can take the tree T rooted at R, and I can take a tree T prime rooted at some node in T, and just look at all its descendants. So, and then there is essentially a new edge relation arrow prime. Okay. This arrow prime is just a subset of the old arrow relation, the edge relation, except that it is restricted to only the descendants of n. And so, by the way, my definition of descendants includes n also. So, there is I have made it reflexive. Okay. And similarly for ancestors also I have made it reflexive. So, this is the notion of a subtree rooted at something. Then we can also talk about extending the tree with a new node, such that the new tree has the same root as the old tree. So, the distinguished root is still the same, except that there is an extra edge for a new node n prime, which was not there in the original set of nodes. So, the new set of nodes capital N prime is just the old set of nodes n union the new n prime. So, you can extend it one leaf at a time. So, and this is an extension that our Tableau construction naturally allows, right. And so, this is a way. And finally, we will say that a tree is finitely branching. Oh, so now when you talk about infinite trees, there is a possibility that you might have an infinite number of branches, you might have an unbounded number of branches, but finite, and you might have infinite paths also. So, we can talk about trees being finitely branching if every node has only a finite set of successors, immediate successors. Yeah, then we will say that the tree is finitely branching. So, the tree could be infinite, and a finitely branching tree could still have an infinite number of paths. Yeah. So, in that sense the number of different branches could be infinite. Okay. Paths could be of infinite length, the number of different branches could be infinite, but any particular node has only a finite number of immediate successors, right. I mean, so that is it is important. The other thing of course is that something that I did not mention, but which we will take for granted, is that this set of nodes n can be at most countably infinite. I mean, we are not taking a set of nodes which might be uncountable or anything. Okay, so, it could be only a countably infinite set of nodes, but then even though the tree is finitely branching, it could actually have an infinite number of different paths, distinct paths. Each it could have both finite and infinite length paths, branches, and so those are, so we are not putting any restrictions on that, right. So, one thing of course, so these are some simple facts as a consequence of these definitions. If the for any tree rooted at R, the descendants of R are exactly the set n, set of nodes, ancestors and so on. These are I mean, these are useless things. These are the usual things, and then a rooted tree is usually acyclic, and basically for all nodes there is no path of length 1 or more from a node to itself, right. So, it is that is the acyclicity condition. So, the notion of self loops is something we eliminated right at the start, right, because we said that L of t is equal to L of s plus 1, and that is not possible unless I mean, unless you exclude self loops. But now we have to this also there is a consequence of all that is also that trees have to be acyclic. The other thing is we will take so let us take any tree, and we will call a node to be infinitary if the set of descendants of that node is an infinite set, right. So, descendants means you are taking all possible finite length paths starting from that node, all possible. So, descendants is synonymous with this reflexive transitive closure of the edge relation. So, this reflexive transitive closure does not go through through infinite length paths, it only looks at all finite length paths, right, that is important. Okay. So, a node is called infinitary if all its descendants if the set of its descendants is infinite, otherwise the node is called finitary. Yeah, but still so a finitely branching tree could have infinitary nodes. So, all that we are saying is that for any node the set of its immediate successors is a finite set, but the set of its descendants need not be finite, right. So, nodes could be infinite. So, one simple lemma that we have is in a finitely branching tree every infinitary node has an infinitary successor. You can think of this the next two these two lemma as essentially some kind of pigeonhole principle generalized to infinite trees. Means the analogy with pigeonholes is, let us look at the standard pigeonhole principle. It is usually defined for finite sets, and you essentially say that if there are n plus 1 elements, n plus 1 balls to be distributed in n boxes, then there is at least one box which has 2 balls, right. And that is, you can start generalizing this for all kinds of finite n's and n plus all kinds of m's and so on and so forth, but you can also go into an infinite set. If I have an infinite collection of balls and I have a finite number n of boxes, then an extended pigeonhole principle would essentially say that there is at least one box with an infinite number of balls in it, right. Okay. But these when you look at, so finitely branching trees are a further weakening of that, because even though a tree might be finitely branching, the number of different branches might still be infinite. Okay. So, actually you have, so the branches correspond to the infinite boxes, and think of putting the individual nodes in the individual boxes, right, distributing the nodes in the boxes, right. So, it is a kind of infinitary pigeonhole principle for finitely branching trees, right. So, in a finitely branching tree, so what we are saying, so this every infinitary node has an infinitary successor is essentially like saying that there is at least one branch. So, actually that it becomes more clear with the next lemma, which is going to use this lemma. Every finitely branching infinite tree has an infinite path, and this is Koenig's lemma, and this essentially says that if I take all these branches as boxes and the nodes as balls, then there is at least one box with an infinite number of balls in it. The main weakening here is that a finitely branching tree need not correspond to only a finite number of boxes. It is finitely branching, but the total number of distinct branches might be infinite, right. So, it is still, so you are looking at a case of an infinite number of balls being put in an infinite number of boxes, but there is this constraint of finitely branching, which somehow seems to indicate that there should be at least one box with an infinite number of balls. Yeah. Okay. So, let us look at the proof of the first lemma. So, all we are saying is that, so we can label the nodes as being each, we can associate the finitary or infinitary property with each node, and we are saying that in a finitely branching tree every infinitary node has an infinitary successor. Supposing not, suppose that is not true, then for there is some infinitary node, which of course it is a finitely branching tree. So, the successors of that node, the set of successors of that node is a finite set, right. So, which means, and if it is if there is an infinitary node which does not have an infinitary successor, then all the successors are finitary. If all the successors are finitary, then each of those successors has only a finite number of descendants, and therefore, I can actually add up all those sets, and I get only I get that the original node therefore must be finitary, which contradicts the assumption that the original node was infinitary, right. So, which means that among the successors of this infinitary node n, there is at least one node which is also infinitary. Yes. Is it clear? Yeah. Okay. So, now let us go to Koenig's lemma proper, which just says that every finitely branching infinite tree has an infinite path. So, again we prove by contradiction, assume that T is a finitely branching infinite rooted tree which has no infinite path. Then firstly the root, the set of descendants of the root is the entire set of nodes. It is an infinite tree, so the root is clearly infinitary. By the previous lemma, the successors of the root, there must be one node which is infinitary at least. Okay. Okay. So, which means that, so R is the root node R is infinitary, and R has an infinitary successor by this previous lemma, which means there exists a maximal path in T, all of whose nodes are infinitary. Okay, because it is an infinite tree and every infinitary node is guaranteed to have an infinitary successor. So, you take this, so from R there exists a maximal path in which all of the nodes are infinitary, which means that that path has to be an infinite path. So, even though the tree might have an infinite number of different paths, there is it is not that. So, the tree can never, if it is finitely branching. So, if the tree is infinitely branching, then all paths could be finite. So, for example, if I were to right. So, for example, here is a, so you can just take a tree with root node 0, and I can have an infinite number of branches, basically 1, 2, 3, 4 blah blah blah. So, an infinitely branching tree where every path can be finite, every path has a length of 1, right. This is an infinitely branching tree. So, this is an infinite tree which has a single infinitary node 0, and all other nodes are, any leaf node is finitary, cannot be infinitary. Yeah. So, what Koenig's lemma says is that, so now if I have finitely, but unfortunately this thing is an infinitely branching node. This node 0 is an infinitely branching node. So, this does not satisfy Koenig's lemma. If I made sure that every node has only a finite number of successors and the tree is still infinite, then even though there might be an infinite number of different branches, there is at least one branch which is an infinite path. It's actually a beautiful generalization of a pigeonhole principle for finitely branching trees. Yeah. So, in fact, what you can do is, so this is actually in the form of an implication, right. It is actually, I can reword Koenig's lemma as every infinite rooted tree is either infinitely branching or is finitely branching and has at least one infinite path. That is your pigeonhole principle for all rooted trees, if you like. Yeah. So, this, so it is actually surprising, the lemma is very basic, but and it is actually widely known, but it is never taught usually in any undergraduate course. Have you guys encountered this lemma before? It is a very simple lemma, but it's somehow people never teach it in any undergraduate course, but it becomes important for our notion of compactness, right. Okay. So, which brings us to the compactness theorem. So, take a countably infinite set of sentences. This infinite set of sentences is satisfiable if all non-empty finite subsets of this set are satisfiable. Okay. The first thing to realize in this theorem is that any countably infinite set has an uncountably infinite number of different subsets. Okay. But of course, out of that uncountable number of different subsets, the number of finite subsets is only countable. All the other subsets are all infinite subsets. I mean, some of this thing can give you a severe headache thinking about it, but the analogy is with real numbers. Okay. Let us take the real numbers. The real numbers basically consist of the rationals and the irrationals. Okay. The rationals are a countably infinite set. Okay. The reals are an uncountably infinite set. Therefore, clearly the set of irrationals is uncountably infinite, right, and it is exactly the same whatever argument you might apply for the reals, to essentially you are looking at an extension of numbers to and cardinalities to infinite sets, right. So, what you are saying is that the number of rationals is really the same as the number of integers or number of naturals, but the number of irrationals is really the same as the number of reals, okay, and it's a notch higher. In the case of your countably infinite sets also, you take any countably infinite set, what we do. So, one thing is clear, no set whether finite or countable or uncountable, no set has the same number of elements as its power set. Okay. This is a simple diagonalization argument which will show that in case a set A can be placed in 1-to-1 correspondence with its power set 2 raised to A, then then I can actually create a diagonalization argument which shows that any kind of that there exists a subset which you have not accounted for. Okay. So, which destroys the notion of a 1-to-1 correspondence. So, this is a very standard thing that you can show. So, one thing you can show is that no set can be placed in 1-to-1 correspondence with its power set, which means no set, the cardinality of any set cannot be the same as the cardinality of its power set, right. But then once you got that the cardinality of a set is different from the cardinality of its power set, we can definitely ask the questions, what is the cardinality of this set of finite subsets of the set, and what is the cardinality of the set of infinite subsets of this set. If the original set is infinite, we can ask these questions. So, in the case of this, and just like you go through these proofs for real numbers and rationals and irrationals, you can go through similar proofs to show that the number of finite subsets of a countably infinite set is actually countable, and the number of infinite subsets is actually uncountable, and therefore, the total number of subsets of an infinite set, of a countably infinite set, is actually uncountably infinite. Okay. So, so I do not want to get into that, but this is so that the compactness theorem says that I just require all the finite subsets to be satisfiable, and I can guarantee that that original infinite set will be satisfiable. Okay. So, let us look at the proof of this theorem. Okay. So, let me start with the set gamma, which is countably infinite, and it has, if it is countably infinite, then basically it can be placed in 1-to-1 correspondence with the naturals, which means I can essentially enumerate the set of formulae in gamma and index them with the naturals. So, I can talk about phi 0, then phi 1, phi 2, I mean all the elements in gamma can be enumerated corresponding to whatever 1-to-1 correspondence with the naturals you may choose to define. Yeah. So, typical for any natural j, phi j is the essentially the j plus 1th element in this enumeration, if you like, right. And now, what I can do is take this enumeration, I can consider all these finite subsets gamma j, for example. So, gamma j just consists of the first j sentences in the enumeration. So, here I have written gamma m, oh okay, should this be m minus 1? Let's look at gamma m, maybe it does not matter, but let us think of gamma m as consisting of phi naught to phi m minus 1, yeah, the first m elements in the enumeration, right. So, one thing is every non-empty finite, okay, I have a peculiar way of sometimes writing proofs, which is that I state claims and I create subproofs. Okay. So, this that you see here, there is a claim which is underlined and in italics, and then there are these two symbols, right turnstile and left turnstile and right turnstile, which actually bracket the proof of only this claim. Yeah. So, that so it's this is like a lot like program structuring. In any kind of structured programming thing, you would like to divide up your program into various functions and then use those functions in some main way. So, these claims are like some functions in a program, and we will see the analogy with programming in the proof theory also that we do, but essentially it is possible to have a nested structure of theorems and proofs, especially of proofs, so that you can have individual claims, subclaims and so on and so forth, and very much like program nesting. Okay, so, here is a claim which actually is not very important. It just says that every non-empty finite subset of gamma, oh by the way, and it also follows the usual scope rules of programming. I mean, so gamma has already been declared in the outer scope, so it is available in the inner scope, yeah, unless it is renamed. Yeah, and so it follows all those structured programming rules. So, every non-empty finite sub, and basically, so all the properties that you have defined before are available in here, follows exactly the program structure that we normally would like to employ. Okay. Every non-empty finite subset of gamma is satisfiable if and only if for every m, gamma m is also satisfiable. Okay. So, this is one thing of course is clear. If every non-empty finite subset of gamma is satisfiable, then clearly each gamma m being a finite subset also is satisfiable. The other thing is, given this particular order of gamma m's, given that there is a particular, so take can you make the same claim that all the finite subsets are also satisfiable. So, we will just go from finite tree. So, you take any finite subset delta. Oh, by the way, this is my notation, subset with subscript f means it is a finite subset. Okay. So, and of course, this is non-empty finite subset, we are only looking at non-empty finite subsets. So, let delta be any non-empty finite subset, then clearly there is an m in which such that delta is also a subset of m. So, delta contains these various formulae from the enumeration phi naught, phi 1, phi 2, phi 3 etcetera, and they are all indexed by the naturals. So, there is a highest index in delta. Okay. So, now I just take gamma m or gamma m plus 1. Okay. So, I take a gamma m or a gamma m plus 1, that will include every sentence chosen in delta. So, delta is a subset of some gamma m, some gamma k. Yeah. So, then since gamma k is satisfiable, we know that any finite subset of gamma k is also satisfiable, because the same truth assignment which was used to satisfy all the sentences in gamma k can be used for all the sentences in delta, and it will be true, right. Okay. So, now our theorem, the proof of the compactness theorem, reduces to essentially showing that if each of the gamma i's is satisfiable, then gamma is also satisfiable. So, what do? I am going to use the tableau method. So, I start with gamma naught. So, gamma naught just consists of that formula phi naught. Okay. Create a tableau for it. The assumption is that gamma is a countably infinite set of propositions in which each subset of gamma is satisfiable. So, a singleton set is also a subset, and so therefore, what does it mean? It means that this tableau rooted at gamma naught, this tableau rooted at gamma naught is essentially a tableau rooted at the formula phi naught, does not close, right. since that means phi naught is satisfiable. So, I have this tableau which essentially starts with phi naught and it might have some closed branches, but the fact that phi naught is satisfiable means that there is at least one open branch. Okay. Now, what do I do? In this open branch, I also add phi 1. Okay. So, I extend it to phi 1. So, now what do? I continue the tableau, phi 1 is some complex formula and I continue this tableau. Okay. This will again have some closed branches, but this whole thing is essentially a tableau for the set phi naught phi 1 and that is a finite set and it is satisfiable and therefore, there must be at least one open branch. Okay. I add phi 3 there and so on. I essentially and then basically then I get an extended tableau which is a tableau for the subset gamma 3 phi naught phi 2 for gamma 2 and then gamma 3 and so on and so forth, right. So, now essentially I start with a tableau T naught, extend it to tableau T 1, extend it to tableau T 2 and so on and so forth, and since each of these gamma m's is a finite set, each of them is satisfiable. So, for each m, tableau T m has at least one open path. Okay. Then by Koenig's lemma and this tableau is a finitely branching tree. Okay. So, there exists an infinite tree such that all the formulas phi I in the set gamma occur at some stage on open paths. So, basically all I am saying is, so we take all the open paths and okay, I should have mentioned that in every open path we put phi 1 here and when you put phi 2 you put it on every open path, because you do not know which one might close and which one not close, right. But what the satisfiability of each finite set assures you that there is always going to be at least one open path, and that open path will have an occurrence of each of the phi i's at some stage or the other, and that will be an infinite path by Koenig's lemma, and it will never close. So, every one of these formulae phi 1 to phi n occur in at least one path. So, the fact that there is an infinite set collection of formulae, the entire gamma occurs in this path which is not closed, and therefore, gamma must be satisfiable, right. Why must gamma be satisfiable? Your tableau construction creates Hintica sets. So, you take right. So, supposing you take this open path starting from phi naught. Yeah. What we have shown yesterday is that if you look at all the formulae there, this is actually a Hintica set H naught, and the addition of phi 1 and an open path here, oh I am sorry, this is an open path here essentially is a Hintica set for phi naught phi 1, and for each gamma m, therefore, if I just collect all the formulas in the path, I get a Hintica set for gamma m. For every m, for every gamma m, there is a Hintica set if I just follow the path. And what we know is that these Hintica sets are always satisfiable. So, you think of this, that application of the first set of tableau rules, and you think of it as collecting all these formulas along the open path, and and what we showed last time was we showed that every Hintikka set is satisfiable, right. Here are Hintikka sets, every Hintikka set is satisfiable, right. So, we showed this last time, and what this open path contains are only Hintikka sets. The path is infinite because it does not close, and by Koenig's lemma, and of course, every element of gamma appears in it, it is an open path and it is a Hintikka set. Remember that the fact that it is an infinite path, so I cannot conclude therefore that it is directly satisfiable. What allows me to conclude that it is satisfiable is the fact that what this path has is an Hintikka set, and all Hintikka sets are satisfiable by this lemma, right. So, essentially the tableau for T the tableau T m has a Hintikka set in it for each m. By Koenig's lemma, since there is an infinite path and it is not closed, but that infinite path, if I collect all the formulas in that infinite path, the set of all formulae that occur in that infinite path is a Hintikka set, and all Hintikka sets are satisfiable, and therefore, this entire path, infinite path, is satisfiable. So, the formulas in this path are satisfiable. Therefore, which means that gamma, which is just a subset of this original Hintikka of this Hintikka set, is also satisfiable, right. So, I think we have formally started logic at a point where you probably do not think things are obvious, right. And so, we have this compactness theorem and it has some fairly serious consequences. One is the notion of inconsistency. So, we defined consistency as this being the same as satisfiability. Okay. So, inconsistency is just lack of consistency, right. But the compactness theorem essentially says that if the set gamma is if you have an infinite set gamma which is consistent, if every finite subset of it is consistent, then this infinite set gamma is also consistent. So, now inconsistency reduces to essentially taking the converses of both sides. Firstly, it is obvious that you have this corollary, right. So, any finite or infinite set of formulae is satisfiable or consistent if and only if all its non-empty finite subsets are satisfiable. Okay. This is a consequence of this compactness theorem, right. So, what this also means for inconsistency is that any finite or infinite set of formulae is inconsistent if and only if there exists at least one non-empty finite subset which is inconsistent, right. So, inconsistency therefore reduces. So, this so essentially so we can think of it as a definition of inconsistency now that we have the compactness theorem. So, we just say that a set gamma is inconsistent if there is some non-empty finite subset which is unsatisfiable. Yeah. Okay. So, oh God. So, I am sorry. Okay. So, one thing is it is clear, satisfiability or consistency, if gamma is consistent, then any subset of it is also consistent. In the case of inconsistency, it works the other way around. You take an inconsistent set and add a few more formulae into it, it still remains inconsistent. So, any superset of an inconsistent set is going to be inconsistent, okay, because the tableau which was used to prove, let us say, the inconsistency of that original set can be used without any change to show that this set is also the superset is also inconsistent. Okay. So, the other simple facts are that any set containing a complementary pair is obviously inconsistent, because it is not going to be, it is never going to become a Hintika set. Okay. And of course, our notion of multiplicative and additive operators give us these two facts. So, we had these notions of multiplicative and additive operators. So, for each binary operator, multiplicative or additive operator of the form, I mean so with components psi and chi, we had a corresponding psi prime and chi prime, right. So, you take this so the notions of inconsistency essentially say that if I take psi prime and chi prime and add it to a set delta, and that set is inconsistent, then just adding phi to delta also makes the set delta union phi inconsistent, right. In the case of the multiplicative operators. In the case of the additive operators, you add only psi prime or you add only phi prime. If both of them are inconsistent, then adding phi makes the set inconsistent, right. I mean, so this is just doing the converses with negations, yeah, starting from the characterization of consistency as a finite or infinite set gamma is consistent if and only if all its finite non-empty subsets are consistent, right. Okay. So, I will stop here. Please digest it. You require more than Digene to digest the compactness theorem. There are some more consequences of the compactness theorem which we will do next time.